Hey guys, welcome to another lecture in Precalculus. So today we're actually going to change it up, and I figured since we're going to start getting into the meat of Precalculus, we might as well switch over to some slides, and I've kind of changed up my setup, so hopefully this might actually be more useful than it used to. So what are we talking about today? Today we're going to be talking about sets, and let's get started with the first slide, the first set. So a set is pretty much a well-defined collection of objects which have elements. So what is a well-defined collection of objects? A well-defined collection of objects simply means that you have boundaries for the values of these objects. So let's take an example set. So let's think about the alphabet. So let's let this set be called A, and it's always denoted by curly braces. So curly braces. So a set A that contains all the elements of the alphabet would go A, B, C, D, and all the way to Z, right? Three dot notation means everything just continue onwards until we hit the next bound. So this is a set. So why is this well defined? Because, well, one, we know all the things that go into an alphabet. So if I asked you if D was part of the alphabet, you'd be able to say D is part of an A. So that is called containing. So A has C, or C is in big A. This can be written as C is an element of A. And if C didn't belong in A, let's say there's some, like, we don't care about numbers, so let's do 1 is not an element of A. So that's some basic notation to keep in mind. So that is an element, and this is not an element. So let's think of another set of things. So let's say the set of numbers. So the set of numbers, let's say n, is equal to everything that starts from negative infinity, right, all the way till 0, and goes all the way till infinity. This would be the set of all possible numbers. Let's talk about notation and how you write sets. So let's take this condition that x is x such that x is positive and even. How do we build a set? So what this is saying is that there's some arbitrary general element of the set where such that this pipe means such that x is positive and even. So what does that mean? So for every element in the set, let's say the set is equal to S, there's an x that is positive, both positive and is even, which means let's start a positive number. So 1, is 1 positive? Yes, but is it even? No. So then it's just every positive even number, right? 2, 4, 6, 8, and so on and so forth. This is the set that we're talking about here. So if we were to go back to the slide from earlier, we were talking about all the positive number, it would just be, if we were to use set builder notation, it would be x such that x, right? It can be any number. So it's such that x is an element of numbers, let's say, for numbers. I'll write that like that, too lazy to erase it. So x such that x is an element of numbers. Now this could be also done for the alphabet. So x such that x is an element of the alphabet, right? So keep in mind that x doesn't have to be a number. It could be anything. It could be a cat, a dog. Really doesn't matter. It's just saying that it's some general element in the set. Okay, so now we're going to talk about all kinds of different types of sets. So sets that you're going to encounter in this course and for the rest of your life if you're going to continue doing any kind of math or physics. And so the first set we're going to explore is the empty set. So the empty set is just as important as 0 is in regular math. So the empty set is just as important as 0 is in regular math. So this is simply a set with no elements, numbers. Say you had a set of numbers. So let's say 1, 2, 3, 4, 5. And then you have to use these numbers such that let's come up with another set S, and we'll use the example from before where x is x such that x is positive and even. So in this case, this is not a null set because and x is an element of A. So x is in A. So what are the positive and even things in A? It's simply 2 and 4. So now let's flip this around a little bit. Let's use the set B such that x is an element of A and x is an element of A and it's negative. So we look over at A and we try to find all the negative elements x such that it's negative. So we see that there's actually no negative elements in this. So this right here is the empty set. This is also called the null set because there's nothing in it. It's a null set. Okay, let's move on to so now we're going to talk about the natural numbers. So the natural numbers are numbers that start at 1 and are positive, and they go onwards and on forth. So it goes all the way up. So not to be confused with other sets that we're going to be talking about. This one's pretty straightforward. I don't think we need to explain this further than it is. It's just all the positive numbers all the way to infinity. And keep in mind, the ellipses mean that it just continues and so forth and so on. So now let's talk about integers. So integers is all the possible numbers that are whole numbers. Now it's important that they're whole numbers. So integers, represented by this bolded z, so this bolded z, starts from all the numbers from negative infinity all the way till 0, all the way till positive infinity, all the way till positive infinity. So these are all the whole numbers. And let me write that down. So integers are whole numbers. Integers are whole numbers, right? That's key. Integers are whole numbers. Whereas what we're going to talk about next in the next slide are rationals. So rationals are numbers that are fractions and such that A, there actually should be a B there. I'm not sure why that's missing. I'm going to add that in right now. Such that A and B are an element of the integer. So what does this mean? This means that any number you can write as a fraction is a rational. So it could be 5 over 2, it could be 1 over half, it could be 3 over 2, it can be 1000 over 40. These are all elements of Q because these numbers can be written as a rational. Now, keep in mind that we know that whole numbers can also be written as a rational, right? So if you have the number 2, the number 2 can also be written as 2 over 1. So the integers are actually a subset. Integers are a subset of Q. So integers are a subset of rationals. So Q being the rationals contain all the integers because you can write all the integers as rationals. Now let's move on to the next one. So let me get rid of that and move slides. And so now we're talking about real numbers. So real numbers are every possible number you can imagine that are part of the rationals, the integers, the natural numbers, right? The rationals, the integers, and the natural numbers. So anything from 1/2 to 1 to -1 to infinity, these are all real numbers. These are all real numbers. So real numbers encompass integers, rationals, and natural numbers. So whereas integers were a subset of rationals and naturals were a subset of real numbers, naturals were a subset of integers, all of those are actually a subset. All of those are actually a subset of real numbers. So real numbers can be anything. Decimals can be anything, right? So let's move on to the next Next one. Okay, so now we have irrational numbers. So what is an irrational number? An irrational number is something that can't be written as a rational number, right? Something that can't be written as a natural number, a rational number. So, which means that q such that x such that x cannot be represented, cannot be written, cannot be represented as a over b. So we've seen that all numbers that we've explored so far can be written as a rational number. So an irrational number is something that can't be written as a over b. So let's take, for instance, some famous irrational numbers such as pi. Pi cannot be written as a rational number. You can't write this as a over b because we've seen that pi is equal to 3.14, so forth, and forever, right? So as far as we know, we can't really write 3.14 because if you could try this yourself, this could be some algebra. You can try to put pi is equal to a over b and then try and find these, and you won't be able to, but this is how you would go about proving it. Whereas if you took something like 10, you know this because 10 can be written as 10 over 1, right? So you have a over b. There are so many other irrational numbers. The square root of 2 is another one. You couldn't solve for one of these variables to be able to create this. And that's why it's an irrational number. It's an irrational number, which is a non-rational real number. So the next slide is interval notation. So now that we have an idea of what these intervals are, these sets are, we need to come up with a way to describe them. So there's three types of notation. So one is an open interval. An open interval is when the set does not include the endpoints. The set does not include the endpoints. So say you had a set of numbers that go 1, 2, 3. An open interval of 1, 2, 3 would be such that it goes from 0 all the way to 4, right? So an open, it doesn't include the endpoints. So we start at 0 and go to 4, but we don't include either of them. And this would be written as 0 and 4, which means we go 1, 2, 3, and we skip the ends. Now, a closed interval for that exact same example would be if we took 1 all the way to 4, whereas we include the endpoints. So we do 1 to 3. So we include the endpoints. So we go 1, square bracket, 3. Now the other one is the example that I accidentally started writing on the other end. If we go to 1 to 4, we could write this as a mixed interval, which is we include the first one, but we exclude the last one, which is counter to my example here, which would be if we include the first one, we go square brackets inclusive, 1, and then we exclude the last one, so we go circle bracket. You'll be seeing this a lot more when we start graphing and when we get into things like functions. So let's move on. We're going to do some examples now to really consolidate your understanding. So here's the question. Write x such that 1 is less than or equal to x is less than or equal to 3 in interval notation. So in this case, we can actually write out the set. So what is this saying? This means that what values are possible? So x can equal 1, x can equal 2, and can x equal 3? No, right? Because x has to be less than 3. So how do we write this in interval notation? Well, we can actually take a guess by just looking at these operators here. So when it says less than or equal, it means that it's inclusive, right? It's inclusive. But when it says less than, strictly less than, it's saying that it's exclusive. When there is no equal sign, it's saying not including, right? Not including. So what does this mean? We start at 1. That includes 1. and it ends at 3, but doesn't include 3. So this is a square bracket, and it goes 1, 3. And that's how you write interval notation for that. So let's move on to another example now. So let's take this case here. Same idea. So it starts at -1, starts at -1, starts at -1, and it goes to 4. But they're both inclusive. So that means it goes -1, -2, -3. Sorry, not -2. This goes to 0. It goes to 1, 2, 3, and 4, inclusive. So the left-hand side, this means the left bound is inclusive. This means the right bound is inclusive. So we get square bracket -1, 4, square bracket, square brackets. Let's do another one. So x such that x is less than 5. So this only has one bound, has a right bound. So let's start with the right side then. Let's start with the right-hand side bound. So this is saying that 5 is inclusive on the right-hand side. So what happens to the left-hand side when it's always less than? When it's always less than, that means it goes all the way down, including infinity, right? Including infinity. So this is one of those cases that you need to know, which is what is infinity? So whenever you have infinity, you always have the open. Infinity is equal to open interval because you can never actually include infinity. So we always use the open interval for infinity. So the set of integers would be like this, right? Because it goes all the way from -infinity to infinity. But you can never actually include those because you're really only counting the numbers that are actually countable. So let's move on to the next one. So these are pretty easy. So you're going to start really picking up pace here. I'm just making sure I go slow and cover everything. So let's do another one. X is greater or equal to -2. So this is the same idea. Let's work up our left-hand side. Our left-hand side would be, where does it start? It starts at -2, and it's inclusive. It's inclusive. And x can be anything greater than that. So we just did this. We go to infinity, and we close it off this way. Is greater or equal to -2. Yep. And so this is it right here. So you're going everything from -2, -1, all the way till infinity. All the way till infinity. And so that's pretty much interval notation summed up for you. So I know this might be on a little longer of a video than you're used to, and I'll be trying to transition my content more into slide-based so you guys have clearer examples and more questions. And if you learned something new, make sure you like, subscribe, and share. And I know I have a lot to improve on, and hopefully it gets better. I'll catch you guys in the next video.